4,000 meters down in the Pacific, a length of cable spent 8 straight months holding its own weight against pressure that would crush a steel drum flat. When engineers hauled part of it back up for inspection, the strength hadn't dropped at all. No measurable loss. The steel section it replaced usually needed inspection and partial swap out every year and a half. This piece didn't need any of that. And the strange part is, the material holding that cable together wasn't steel at all. It was carbon, arranged so precisely that it barely behaves like a normal material anymore. That deep-sea test is where this story actually proves itself. But to understand why it matters, we need to back up and look at what a Chinese research team built and why it's making steel producers nervous. In 2024, a team working out of the Institute of Metal Research at the Chinese Academy of Sciences, alongside materials scientists at Tsinghua University, published results on a carbon nanotube fiber that tested at over 3,000 megapascals of tensile strength. Standard structural steel tops out around 400. That puts this material at roughly 8 times the strength of the steel holding up your average building or bridge, while weighing about 1/5 as much for the same volume. On paper, that's not a small improvement. That's a different category of material entirely. Here's the number that actually matters more than the headline strength figure, though. How well that strength held up once the material stopped being a small lab sample. A 1-meter strand tested in Shenyang kept its strength within a few percentage points of the tiny original test pieces. That sounds like a minor technical detail, but it's the exact thing that's killed almost every previous carbon nanotube breakthrough before it left the lab. To see why that matters, you have to understand what a carbon nanotube actually is and why scientists have been excited about them for over 2 decades without ever building anything useful out of them. A single nanotube is a cylinder of carbon atoms, just a few nanometers wide, arranged in a seamless hexagonal lattice. Individually, they're absurdly strong. Tests have put single nanotubes at anywhere from 50 to over 100 times stronger than steel for their size. The problem was never the individual tube. The problem was gluing millions of them together into something you could actually hold without losing most of that strength in the process. Earlier attempts bundled nanotubes together using weak intermolecular forces. Between the tubes, think of trying to build a rope out of individually unbreakable threads, but held together with nothing stronger than static cling. The rope held together, technically, but the moment you pulled hard, it failed at those weak connection points, long before any individual thread came close to its actual limit. That's why decades of carbon research produced amazing single-fiber numbers in academic papers, and almost nothing you could build a bridge cable or an aircraft panel out of. What the Chinese team changed was the bonding itself. Instead of relying on those weak forces between tubes, they developed a way to chemically link the tubes end to end and side to side at the molecular level, so that a pulling force gets transferred directly from one tube into the next, rather than getting absorbed and lost at a weak joint. That's the actual breakthrough here. Not a new form of carbon, but a new way of connecting carbon to itself, so the strength of the individual tube survives the trip up to something huge. It's worth understanding why steel has been so hard to displace in the first place. Because the flaw this new material is aimed at isn't really about weakness. It's about a hard ceiling nobody's ever found a way past. Steel earned its dominance over roughly the last 200 years because it does something almost nothing else does at scale. It fails predictably. Overload a steel beam, and it bends first visibly. Before it breaks a warning sign that saved countless lives on bridges and buildings where engineers can spot a sagging beam and close things down before catastrophe. That predictability, plus a century and a half of shared engineering standards, is why a bridge built in Rotterdam and one built in Seoul can be designed using the same trusted math. But steel has a limit baked into its atomic structure that no amount of alloying has ever fully solved. Every batch of steel, no matter how carefully it's made, contains microscopic flaws in the crystal lattice, tiny gaps and dislocations invisible to the eye, but very real under a microscope. Those flaws are where cracks start. You can push steel's strength higher by adding nickel or chromium, but the weight stays exactly where it was, which is why a steel-framed skyscraper can end up spending well over half its structural budget, just supporting its own bulk before it carries a single occupant. Every extra ton of steel holding up more steel is dead weight. That ceiling on strength to weight has shaped nearly every large structure built in the last century, and until now, nobody had a material that could realistically break through it at any usable scale. Which brings the story back to that cable at the bottom of the ocean. In 2025, China's National Deep Sea Center swapped a section of steel cable on one of its long-term ocean monitoring buoys for a strand of this new carbon nanotube material as part of a routine equipment refresh. Over 8 months at depths beyond 3,000 meters, under constant pressure, saltwater corrosion, and repeated temperature swings, 3 things that make ocean engineering a genuinely brutal proving ground, the replacement cable showed no measurable drop in strength. That's meaningfully different from a controlled lab result, because ocean environments have a long history of humbling materials that looked flawless on a bench. The full dataset from that trial, tension logs, temperature readings, inspection photos, was published on an open national data platform. So independent researchers anywhere could check the numbers rather than take the claim on faith. That kind of verified field performance is exactly what turns a material from an academic curiosity into something industry actually bets money on, and the money has clearly started moving. More than 140 international patent families now cite the core bonding technique behind this fiber, filed across China, the United States, Germany, and South Korea, the kind of legal and financial commitment companies don't make on something they consider a novelty. China Baoyu Steel Group, the largest steel producer on the planet, announced a joint research effort worth roughly $200 million in early 2026 aimed at developing hybrid steel nanotube products, essentially choosing to help build whatever eventually challenges its own core business rather than get blindsided by it. COMAC, China's commercial aircraft manufacturer, confirmed it's testing the material for interior components on a narrow-body jet. CATL is evaluating it for battery casings, where every gram shaved off directly extends a vehicle's driving range. In South Korea, POSCO opened a dedicated lab specifically to benchmark the material against its own advanced steel alloys. And China's Ministry of Industry and Information Technology added advanced carbon nanomaterials to its official list of strategic materials in 2025, which unlocks faster permitting and preferential financing, government backing that doesn't guarantee commercial success, but does remove one of the slowest bottlenecks new materials usually face. None of this means the material is cheap, and it's worth being upfront about that instead of glossing over it. Right now, it costs roughly 40 times more per kilogram than standard structural steel, and production is still capped around 2 tons a month across every facility in China combined, nowhere close to the volume needed to meaningfully dent global steel demand. But cost per kilogram is the wrong way to measure this material, because it ignores the 80% weight reduction entirely. Once you calculate cost per unit of strength delivered rather than cost per kilogram of raw material, the gap narrows sharply, and in some applications, it effectively disappears. That's especially true anywhere weight itself carries a direct cost aerospace engineers routinely pay. 10 times the price or more for every kilogram they can shave off a design, because every kilogram not spent lifting structure is a kilogram available for cargo, fuel, or range. By that logic, a material that's 40 times more expensive, but a fifth of the weight, isn't a luxury item. It's a bargain in exactly the applications where it's being tested first. Durability tells a similar story. In lab testing, the material survived more than 10 million stress cycles without measurable degradation, roughly 3 times what comparable high-strength steel cable manages before cracks begin to form. That kind of fatigue resistance, holding up under repeated stress rather than just one big load, is what actually determines whether something is useful for the real world instead of just impressive in a single test. It's also worth being honest about how much is still unresolved. Batch-to-batch quality control remains inconsistent strength, can vary by as much as 15% depending on ambient humidity during the bonding process, which means a factory can't yet guarantee identical performance from one production run to the next. No international building code currently has a framework for certifying a material like this. So any structural application in the US or EU would need years of testing before regulatory approval. The raw carbon nanotube feedstock itself is still a bottleneck, since only a handful of facilities worldwide can produce it at the purity this process needs. And perhaps most importantly, there's no long-term weathering data yet. Steel earned the trust it has today through a century and a half of documented failures, each one feeding back into safer standards. This material hasn't had that century yet, and there's no shortcut around simply letting time pass while it accumulates a track record. None of those gaps change what the lab and field results have already shown is technically possible. They mark the distance between what works and what's ready to scale, which is as much a question of investment, manufacturing capacity, and regulatory patience as it is of materials science. If production scales the way current spending suggests it might, industry analysts project this material could take up to 15% of the high-performance steel cable market. By 2035, a market currently worth around $9 billion a year, with early adoption concentrated exactly where it's already happening: deep-sea equipment and orbital tether systems. To environments where every kilogram saved has an immediate, measurable payoff rather than a theoretical one, there's also a quieter question sitting underneath all of this, about who actually gets to use a material like this once it does scale. The places that would benefit most from lighter, stronger structures: coastal regions facing rising seas, mountainous terrain where hauling heavy steel is its own logistical nightmare. Disaster zones that need to rebuild fast are often the places with the least access to advanced manufacturing in the first place. Right now, large parts of Southeast Asia and East Africa have no domestic access to this material at any price. Whether that gap closes as production scales, or simply hardens into another advantage held by whoever manufactures it first, is a separate story from the engineering itself, and it's one worth watching just as closely. What's actually new here isn't just a strong material. Every major leap in structural engineering, from cast iron to reinforced concrete to modern steel alloys, quietly redrew the boundaries of what could physically get built. What's new is a material that finally breaks the 2-century-old link between strength and weight that steel could never fully escape. Whether it ends up in bridges and skyscrapers or stays confined to aerospace panels and deep-sea cables for another decade, while cost and code catch up to the chemistry, depends less on whether the material works, since the ocean has already answered that question, and more on how fast the rest of the world decides to build around it.